Brazing is a metal joining process whereby a filler metal is heated above melting point and distributed between two or more close-fitting parts by capillary action. The filler metal is brought slightly above its melting temperature while protected by a suitable atmosphere, usually a flux. It then flows over the base metal and is then cooled to join the workpieces together. It is similar to soldering, except the temperatures used to melt the filler metal are higher for brazing. Fundamentals: in order to obtain high-quality brazed joints, parts must be closely fitted, and the base metals must be exceptionally clean and free of oxides. In most cases, joint clearances of 0.03 to 0.08 mm are recommended for the best capillary action and joint strength. However, in some brazing operations it is not uncommon to have joint clearances around 0.6 mm. Cleanliness of the brazing surfaces is also important, as any contamination can cause poor wetting. The two main methods for cleaning parts, prior to brazing, are chemical cleaning and abrasive or mechanical cleaning. In the case of mechanical cleaning, it is important to maintain the proper surface roughness as wetting on a rough surface occurs much more readily than on a smooth surface of the same geometry. Another consideration that cannot be overlooked is the effect of temperature and time on the quality of brazed joints. As the temperature of the braze alloy is increased, the alloying and wetting action of the filler metal increases as well. In general, the brazing temperature selected must be above the melting point of the filler metal. However, there are several factors that influence the joint designer's temperature selection. The best temperature is usually selected so as to be the lowest possible braze temperature, minimize any heat effects on the assembly, keep filler metal-base metal interactions to a minimum, and maximize the life of any fixtures or jigs used. In some cases, a higher temperature may be selected to allow for other factors in the design. The effect of time on the brazed joint primarily affects the extent to which the aforementioned effects are present. However, in general most production processes are selected to minimize brazing time and the associated costs. This is not always the case, however, since in some non-production settings, time and cost are secondary to other joint attributes. Flux: in the case of brazing operations not contained within an inert or reducing atmosphere environment, flux is required to prevent oxides from forming while the metal is heated. The flux also serves the purpose of cleaning any contamination left on the brazing surfaces. Flux can be applied in any number of forms including flux paste, liquid, powder or pre-made brazing pastes that combine flux with filler metal powder. Flux can also be applied using brazing rods with a coating of flux, or a flux core. In either case, the flux flows into the joint when applied to the heated joint and is displaced by the molten filler metal entering the joint. Excess flux should be removed when the cycle is completed because flux left in the joint can lead to corrosion, impede joint inspection, and prevent further surface finishing operations. Phosphorus-containing brazing alloys can be self-fluxing when joining copper to copper. Fluxes are generally selected based on their performance on particular base metals. To be effective, the flux must be chemically compatible with both the base metal and the filler metal being used. Self-fluxing phosphorus filler alloys produce brittle phosphides if used on iron or nickel. As a general rule, longer brazing cycles should use less active fluxes than short brazing operations. Filler materials: a variety of alloys are used as filler metals for brazing depending on the intended use or application method. In general, braze alloys are made up of 3 or more metals to form an alloy with the desired properties. The filler metal for a particular application is chosen based on its ability to wet the base metals, withstand the surface conditions required, and melt at a lower temperature than the base metals or at a very specific temperature. Braze alloy is generally available as rod, ribbon, powder, paste, cream, wire and pre-forms. Depending on the application, the filler material can be pre-placed at the desired location or applied during the heating cycle. For manual brazing, wire and rod forms are generally used as they are the easiest to apply while heating. In the case of furnace brazing, alloy is usually placed beforehand since the process is usually highly automated. Some of the more common types of filler metals used are aluminum silicon, copper, copper silver, copper zinc, gold silver, nickel alloy, silver, amorphous brazing foil using nickel, iron, copper, silicon, boron, phosphorus, etc. Atmosphere. As brazing work requires high temperatures, oxidation of the metal's surface occurs in an oxygen-containing atmosphere. This may necessitate the use of an atmospheric environment other than air. The commonly used atmospheres are air, simple and economical. Many materials susceptible to oxidation and buildup of scale. Acid cleaning bath or mechanical cleaning can be used to remove the oxidation after work. Flux tends to be employed to counteract the oxidation, but it may weaken the joint. Combusted fuel gas, 87% N2, 11 euro 12% CO2, 5 to 1% CO, 5 to 1% H2. For silver, copper phosphorus and copper zinc filler metals. For brazing copper and brass. Combusted fuel gas, 70 euro 71% N2, 5 euro 6% CO2, 9 euro 10% CO, 14 euro 15% H2. For copper, silver, copper phosphorus and copper zinc filler metals. For brazing copper, brass, nickel alloys, Monal, medium carbon steels. Combusted fuel gas, 73 euro 75% N2, 10 euro 11% CO, 15 euro 16% H2. For copper, silver, copper phosphorus and copper zinc filler metals. For brazing copper, brass, low nickel alloys, Monal, medium and high carbon steels. Combusted fuel gas, 41 euro 45% N2, 17 euro 19% CO, 38 euro 40% H2. For copper, silver, copper phosphorus and copper zinc filler metals. For brazing copper, brass, low nickel alloys, medium and high carbon steels. Ammonia, dissociated ammonia can be used for many types of brazing and annealing. Inexpensive. For copper, silver, nickel, copper phosphorus and copper zinc filler metals. For brazing copper, brass, nickel alloys, Monal, medium and high carbon steels and chromium alloys. Nitrogen plus hydrogen, cryogenic or purified, 70 euro 99% N2, 1 euro 30% H2. For copper, silver, nickel, copper phosphorus and copper zinc filler metals. Nitrogen plus hydrogen plus carbon monoxide, cryogenic or purified, 70 euro 99% N2, 2 euro 20% H2, 1 euro 10% CO. For copper, silver, nickel, copper phosphorus and copper zinc filler metals. For brazing copper, brass, low nickel alloys, medium and high carbon steels. Nitrogen, cryogenic or purified, non-oxidizing, economical. At high temperatures can react with some metals, for example certain steels, forming nitrides. For copper, silver, nickel, copper phosphorus and copper zinc filler metals. For brazing copper, brass, low nickel alloys, Monal, medium and high carbon steels. Hydrogen, strong deoxidizer, highly thermally conductive. Can be used for copper brazing and annealing steel. May cause hydrogen embrittlement to some alloys. For copper, silver, nickel, copper phosphorus and copper zinc filler metals. For brazing copper, brass, nickel alloys, Monal, medium and high carbon steels and chromium alloys, cobalt alloys, tungsten alloys, and carbides. Inorganic vapors, special purpose. Can be mixed with atmospheres AWS 1 euro 5 to replace flux. Used for silver brazing of brasses. Noble gas, non-oxidizing, more expensive than nitrogen. Inert. Parts must be very clean, gas must be pure. For copper, silver, nickel, copper phosphorus and copper zinc filler metals. For brazing copper, brass, nickel alloys, Monal, medium and high carbon steels chromium alloys, titanium, zirconium, hafnium. Noble gas plus hydrogen, vacuum, requires evacuating the work chamber. Expensive. Unsuitable for metals with high vapor pressure, for example silver, zinc, phosphorus, cadmium, and manganese. used for highest quality joints, for example aerospace applications. Common techniques. Torch brazing. Torch brazing is by far the most common method of mechanized brazing in use. It is best used in small production volumes or in specialized operations, and in some countries, it accounts for a majority of the brazing taking place. There are three main categories of torch brazing in use: manual, machine, and automatic torch brazing. Manual torch brazing is a procedure where the heat is applied using a gas flame placed on or near the joint being brazed. The torch can either be handheld or held in a fixed position depending on whether the operation is completely manual or has some level of automation. Manual brazing is most commonly used on small production volumes or in applications where the part size or configuration makes other brazing methods impossible. The main drawback is the high labor cost associated with the method as well as the operator skill required to obtain quality brazed joints. The use of flux or self-fluxing material is required to prevent oxidation. Torch brazing of copper can be done without the use of flux if it is brazed with a torch using oxygen and hydrogen gas, rather than oxygen and other flammable gases. Machine torch brazing is commonly used where a repetitive braze operation is being carried out. This method is a mix of both automated and manual operations with an operator often placing brazes material, flux and jigging parts while the machine mechanism carries out the actual braze. The advantage of this method is that it reduces the high labor and skill requirement of manual brazing. The use of flux is also required for this method as there is no protective atmosphere, and it is best suited to small to medium production volumes. Automatic torch brazing is a method that almost eliminates the need for manual labor in the brazing operation, except for loading and unloading of the machine. The main advantages of this method are, a high production rate, uniform braze quality, and reduced operating cost. The equipment used is essentially the same as that used for machine torch brazing, with the main difference being that the machinery replaces the operator in the part preparation. Furnace brazing. Furnace brazing is a semi-automatic process used widely in industrial brazing operations due to its adaptability to mass production and use of unskilled labor. There are many advantages of furnace brazing over other heating methods that make it ideal for mass production. One main advantage is the ease with which it can produce large numbers of small parts that are easily jigged or self-locating. The process also offers the benefits of a controlled heat cycle and no need for post-braze cleaning. Common atmospheres used include, inert, reducing or vacuum atmospheres, all of which protect the part from oxidation. Some other advantages include, low unit cost when used in mass production, close temperature control, and the ability to braze multiple joints at once. Furnaces are typically heated using either electric, gas or oil depending on the type of furnace and application. However, some of the disadvantages of this method include, high capital equipment cost, more difficult design considerations and high power consumption. There are four main types of furnaces used in brazing operations: batch type, continuous, retort with controlled atmosphere, and vacuum. Batch-type furnaces have relatively low initial equipment costs and heat each part load separately. It is capable of being turned on and off at will, which reduces operating expenses when not in use. These furnaces are well suited to medium to large volume production and offer a large degree of flexibility in type of parts that can be brazed. Either controlled atmospheres or flux can be used to control oxidation and cleanliness of parts. Continuous-type furnaces are best suited to a steady flow of similar-sized parts through the furnace. These furnaces are often conveyor-fed, allowing parts to be moved through the hot zone at a controlled speed. It is common to use either controlled atmosphere or pre-applied flux in continuous furnaces. In particular, these furnaces offer the benefit of very low manual labor requirements and so are best suited to large-scale production operations. Retort-type furnaces differ from other batch-type furnaces in that they make use of a sealed lining called a retort. The retort is generally sealed with either a gasket or is welded shut and filled completely with the desired atmosphere and then heated externally by conventional heating elements. Due to the high temperatures involved, the retort is usually made of heat-resistant alloys that resist oxidation. Retort furnaces are often either used in a batch or semi-continuous versions. Vacuum furnaces is a relatively economical method of oxide prevention and is most often used to braze materials with very stable oxides that cannot be brazed in atmosphere furnaces. Vacuum brazing is also used heavily with refractory materials and other exotic alloy combinations unsuited to atmosphere furnaces. Due to the absence of flux or a reducing atmosphere, the part cleanliness is critical when brazing in a vacuum. The three main types of vacuum furnace are single-wall hot retort, double-walled hot retort, and cold-wall retort. Typical vacuum levels for brazing range from pressures of 1.3 to 0.13 pascals to 0.00013 pascals or lower. Vacuum furnaces are most commonly batch type, and they are suited to medium and high production volumes. Silver brazing, sometimes known as a silver soldering or hard soldering, is brazing using a silver alloy-based filler. These silver alloys consist of many different percentages of silver and other metals, such as copper, zinc and cadmium. Brazing is widely used in the tool industry to fasten hard metal tips to tools such as saw blades. Pre-tinning is often done. The braze alloy is melted onto the hard metal tip, which is placed next to the steel and remelted. Pre-tinning gets around the problem that hard metals are hard to wet. Brazed hard metal joints are typically 2 to 7 mils thick. The braze alloy joins the materials and compensates for the difference in their expansion rates. In addition, it provides a cushion between the hard carbide tip and the hard steel which softens impact and prevents tip loss and damage, much as the suspension on a vehicle helps prevent damage to both the tires and the vehicle. Finally, the braze alloy joins the other two materials to create a composite structure, much as layers of wood and glue create plywood. The standard for braze joint strength in many industries is a joint that is stronger than either base material, so that when under stress, one or other of the base materials fails before the joint. One special silver brazing method is called pin brazing or pin brazing. It has been developed especially for connecting cables to railway track or for cathodic protection installations. The method uses a silver and flux-containing brazing pin which is melted down in the eye of a cable lug. The equipment is normally powered from batteries. Braze welding is the use of a bronze or brass filler rod coated with flux to join steel workpieces. The equipment needed for braze welding is basically identical to the equipment used in brazing. Since braze welding usually requires more heat than brazing, acetylene or methylacetylene propane gas fuel is commonly used. The name comes from the fact that no capillary action is used. Braze welding has many advantages over fusion welding. It allows the joining of dissimilar metals, minimization of heat distortion, and can reduce the need for extensive preheating. Additionally, since the metals joined are not melted in the process, the components retain their original shape. Edges and contours are not eroded or changed by the formation of a fillet. Another effect of braze welding is the elimination of stored-up stresses that are often present in fusion welding. This is extremely important in the repair of large castings. The disadvantages are the loss of strength when subjected to high temperatures and the inability to withstand high stresses. Carbide, cermet and ceramic tips are plated and then joined to steel to make tipped bandsaws. The plating acts as a braze alloy. Cast iron welding. The welding of cast iron is usually a brazing operation, with a filler rod made chiefly of nickel being used, although true welding with cast iron rods is also available. Ductile cast iron pipe may be also cut welded, a process which connects joints by means of a small copper wire fused into the iron when previously ground down to the bare metal, parallel to the iron joints being formed as per hub pipe with neoprene gasket seals. The purpose behind this operation is to use electricity along the copper for keeping underground pipes warm in cold climates. Vacuum brazing. Vacuum brazing is a material joining technique that offers significant advantages: extremely clean, superior, flux-free braze joints of high integrity and strength. The process can be expensive because it must be performed inside a vacuum chamber vessel. Temperature uniformity is maintained on the workpiece when heating in a vacuum, greatly reducing residual stresses due to slow heating and cooling cycles. This, in turn, can significantly improve the thermal and mechanical properties of the material, thus providing unique heat treatment capabilities. One such capability is heat treating or age hardening the workpiece while performing a metal joining process, all in a single furnace thermal cycle. Vacuum brazing is often conducted in a furnace. This means that several joints can be made at once because the whole workpiece reaches the brazing temperature. The heat is transferred using radiation, as many other methods cannot be used in a vacuum. Dip brazing. Dip brazing is especially suited for brazing aluminum because air is excluded, thus preventing the formation of oxides. The parts to be joined are fixtured and the brazing compound applied to the mating surfaces, typically in slurry form. Then the assemblies are dipped into a bath of molten salt which functions both as heat transfer medium and flux. Heating methods. There are many heating methods available to accomplish brazing operations. The most important factor in choosing a heating method is achieving efficient transfer of heat throughout the joint and doing so within the heat capacity of the individual base metals used. The geometry of the brazed joint is also a crucial factor to consider, as is the rate and volume of production required. The easiest way to categorize brazing methods is to group them by heating method. Here are some of the most common: torch brazing, furnace brazing, induction brazing, dip brazing, resistance brazing, infrared brazing, blanket brazing, electron beam and laser brazing, braze welding. Advantages and disadvantages. Brazing has many advantages over other metal joining techniques, such as welding. Since brazing does not melt the base metal of the joint, it allows much tighter control over tolerances and produces a clean joint without the need for secondary finishing. Additionally, dissimilar metals and non-metals can be brazed. In general, brazing also produces less thermal distortion than welding due to the uniform heating of a brazed piece. Complex and multi-part assemblies can be brazed cost-effectively. Welded joints must sometimes be ground flush, a costly secondary operation that brazing does not require because it produces a clean joint. Another advantage is that the brazing can be coated or clad for protective purposes. Finally, brazing is easily adapted to mass production and it is easy to automate because the individual process parameters are less sensitive to variation. One of the main disadvantages is the lack of joint strength as compared to a welded joint due to the softer filler metals used. The strength of the brazed joint is likely to be less than that of the base metal, S, but greater than the filler metal. Another disadvantage is that brazed joints can be damaged under high service temperatures. Brazed joints require a high degree of base metal cleanliness when done in an industrial setting. Some brazing applications require the use of adequate fluxing agents to control cleanliness. The joint color is often different from that of the base metal, creating an aesthetic disadvantage. Filler metals. Some brazes come in the form of trifoils, laminated foils of a carrier metal clad with a layer of braze at each side. The center metal is often copper. Its role is to act as a carrier for the alloy, to absorb mechanical stresses due to, for example, differential thermal expansion of dissimilar materials, and to act as a diffusion barrier. Braze families. Brazing alloys form several distinct groups. The alloys in the same group have similar properties and uses. Pure metals, unalloyed. Often noble metals are silver, gold, palladium. Ag-Cu, good melting properties. Silver enhances flow. Eutectic alloy used for furnace brazing. Copper-rich alloys prone to stress cracking by ammonia. Ag-Zn, similar to Cu-Zn, used in jewelry due to high silver content to be compliant with hallmarking. Color matches silver. Resistant to ammonia containing silver cleaning fluids. Cu-Zn, general purpose, used for joining steel and cast iron. Corrosion resistance usually inadequate for copper, silicon bronze, copper nickel, and stainless steel. Reasonably ductile. High vapor pressure due to volatile zinc, unsuitable for furnace brazing. Copper-rich alloys prone to stress cracking by ammonia. Ag-Cu-Zn, lower melting point than Ag-Cu for same Ag content. Combines advantages of Ag-Cu and Cu-Zn. At above 40% Zn the ductility and strength drop, so only lower zinc alloys of this type are used. At above 25% zinc, less ductile copper zinc and silver zinc phases appear. Copper content above 60% yields reduced strength and liquidus above 900 degrees Celsius. Silver content above 85% yields reduced strength, high liquidus and high cost. Copper-rich alloys prone to stress cracking by ammonia. Silver-rich brazes are hallmarkable and used in jewelry. Alloys with lower silver content are used for engineering purposes. Alloys with copper-zinc ratio of about 60-40 contain the same phases as brass and match its color. They are used for joining brass. Small amount of nickel improves strength and corrosion resistance and promotes wetting of carbides. Addition of manganese together with nickel increases fracture toughness. Addition of cadmium yields Ag2ZnCd alloys with improved fluidity and wetting and lower melting point. However, cadmium is toxic. Addition of tin can play mostly the same role. Cu-P, widely used for copper and copper alloys. Does not require flux for copper. Can be also used with silver, tungsten, and molybdenum. Copper-rich alloys prone to stress cracking by ammonia. Ag-Cu-P, like Cu-P, with improved flow. Better for larger gaps. More ductile, better electrical conductivity. Copper-rich alloys prone to stress cracking by ammonia. Or Ag, noble metals. Used in jewelry. Or Cu, continuous series of solid solutions. Readily wet many metals, including refractory ones. Narrow melting ranges, good fluidity. Frequently used in jewelry. Alloys with 40–90% of gold harden on cooling but stay ductile. Nickel improves ductility. Silver lowers melting point but worsens corrosion resistance. To maintain corrosion resistance, gold has to be kept above 60%. High temperature strength and corrosion resistance can be improved by further alloying, for example with chromium, palladium, manganese and molybdenum. Addition of vanadium allows wetting ceramics. Low vapor pressure. Or Ni, continuous series of solid solutions. Wider melting range than or Cu alloys but better corrosion resistance and improved wetting. Frequently alloyed with other metals to reduce proportion of gold while maintaining properties. Copper may be added to lower gold proportion, chromium to compensate for loss of corrosion resistance, and boron for improving wetting impaired by the chromium. Generally no more than 35% Ni is used, as higher Ni ratios have too wide melting range. Low vapor pressure. Or PD, improved corrosion resistance over or Cu and or Ni alloys. Used for joining superalloys and refractory metals for high temperature applications, for example jet engines. Expensive. May be substituted for bicobalt-based brazes. Low vapor pressure. PD, good high temperature performance, high corrosion resistance, high strength. Usually alloyed with nickel, copper, or silver. Forms solid solutions with most metals, does not form brittle intermetallics. Low vapor pressure. Ni, nickel alloys, even more numerous than silver alloys. High strength. Lower cost than silver alloys. Good high temperature performance, good corrosion resistance in moderately aggressive environments. Often used for stainless steels and heat-resistant alloys. Embrittled with sulfur and some lower melting point metals, for example zinc. Boron, phosphorus, silicon and carbon lower melting point and rapidly diffuse to base metals. This allows diffusion brazing and allows the joint to be used above the brazing temperature. Borides and phosphides form brittle phases. Amorphous preforms can be made by rapid solidification. Cobalt alloys. Good high temperature corrosion resistance, possible alternative to or PD brazes. Low workability at low temperatures, preforms prepared by rapid solidification. AlC, for brazing aluminium. Active alloys, containing active metals, for example titanium or vanadium. Used for brazing non-metallic materials, for example graphite or ceramics. Role of elements, some additives and impurities act at very low levels. Both positive and negative effects can be observed. Strontium at levels of 0.01% refines grain structure of aluminium. Beryllium and bismuth at similar levels help disrupt the passivation layer of aluminium oxide and promote wetting. Carbon at 0.1% impairs corrosion resistance of nickel alloys. Aluminium can embrittle mild steel at 0.001%, phosphorus at 0.01%. In some cases, especially for vacuum brazing, high-purity metals and alloys are used. 99.99% and 99.999% purity levels are available commercially. Care has to be taken to not introduce deleterious impurities from joint contaminations or by dissolution of the base metals during brazing. Melting behavior: alloys with larger span of solidus liquidus temperatures tend to melt through a mushy state, where the alloy is a mixture of solid and liquid material. Some alloys show tendency to liquation, separation of the liquid from the solid portion. For these, the heating through the melting range has to be sufficiently fast to avoid this effect. Some alloys show extended plastic range, when only a small portion of the alloy is liquid and most of the material melts at the upper temperature range. These are suitable for bridging large gaps and for forming fillets. Highly fluid alloys are suitable for penetrating deep into narrow gaps and for brazing tight joints with narrow tolerances, but are not suitable for filling larger gaps. Alloys with wider melting range are less sensitive to non-uniform clearances. When the brazing temperature is suitably high, brazing and heat treatment can be done in a single operation simultaneously. Eutectic alloys melt at single temperature, without mushy region. Eutectic alloys have superior spreading. Non-eutectics in the mushy region have high viscosity and at the same time attack the base metal, with correspondingly lower spreading force. Fine grain size gives eutectics both increased strength and increased ductility. Highly accurate melting temperature allows joining process to be performed only slightly above the alloy's melting point. On solidifying, there is no mushy state where the alloy appears solid but is not yet. The chance of disturbing the joint by manipulation in such state is reduced. Eutectic behavior is especially beneficial for solders. Metals with fine grain structure before melting provide superior wetting to metals with large grains. Alloying additives can be added to refine grain structure, and the preforms or foils can be prepared by rapid quenching. Very rapid quenching may provide amorphous metal structure, which possess further advantages. Interaction with base metals. For successful wetting, the base metal has to be at least partially soluble in at least one component of the brazing alloy. The molten alloy therefore tends to attack the base metal and dissolve it, slightly changing its composition in the process. The composition change is reflected in the change of the alloy's melting point and the corresponding change of fluidity. For example, some alloys dissolve both silver and copper. Dissolved silver lowers their melting point and increases fluidity, copper has the opposite effect. The melting point change can be exploited. As the remelt temperature can be increased by enriching the alloy with dissolved base metal, step brazing using the same braze can be possible. Alloys that do not significantly attack the base metals are more suitable for brazing thin sections. Non-homogeneous microstructure of the braze may cause non-uniform melting and localized erosions of the base metal. Wetting of base metals can be improved by adding a suitable metal to the alloy. Tin facilitates wetting of iron, nickel, and many other alloys. Copper wets ferrous metals that silver does not attack. Copper-silver alloys can therefore braze steels silver alone won't wet. Zinc improves wetting of ferrous metals, indium as well. Aluminium improves wetting of aluminium alloys. For wetting of ceramics, reactive metals capable of forming chemical compounds with the ceramic can be added to the braze. Dissolution of base metals can cause detrimental changes in the brazing alloy. For example, aluminium dissolved from aluminium bronzes can embrittle the braze. Addition of nickel to the braze can offset this. The effect works both ways. There can be detrimental interactions between the braze alloy and the base metal. Presence of phosphorus in the braze alloy leads to formation of brittle phosphides of iron and nickel. Phosphorus-containing alloys are therefore unsuitable for brazing nickel and ferrous alloys. boron tends to diffuse into the base metals, especially along the grain boundaries, and may form brittle borides. Carbon can negatively influence some steels. Care has to be taken to avoid galvanic corrosion between the braze and the base metal, and especially between dissimilar base metals being brazed together. Formation of brittle intermetallic compounds on the alloy interface can cause joint failure. This is discussed more in depth with solders. The potentially detrimental phases may be distributed evenly through the volume of the alloy, or be concentrated on the braze base interface. A thick layer of interfacial intermetallics is usually considered detrimental due to its commonly low fracture toughness and other subpar mechanical properties. In some situations, for example die attaching, it however does not matter much as silicon chips are not typically subjected to mechanical abuse. On wetting, brazes may liberate elements from the base metal. For example, aluminium silicon braze wet silicon nitride dissociates the surface so it can react with silicon, and liberates nitrogen, which may create voids along the joint interface and lower its strength. Titanium-containing nickel-gold braze wet silicon nitride and reacts with its surface, forming titanium nitride and liberating silicon. Silicon then forms brittle nickel silicides and eutectic gold silicon phase. The resulting joint is weak and melts at much lower temperature than may be expected. Metals may diffuse from one base alloy to the other one, causing embrittlement or corrosion. An example is diffusion of aluminium from aluminium bronze to a ferrous alloy when joining these. A diffusion barrier, for example a copper layer, can be used. A sacrificial layer of a noble metal can be used on the base metal as an oxygen barrier, preventing formation of oxides and facilitating fluxless brazing. During brazing, the noble metal layer dissolves in the filler metal. Copper or nickel plating of stainless steels performs the same function. In brazing copper, a reducing atmosphere may react with the oxygen residues in the metal, which are present as cuprous oxide inclusions, and cause hydrogen embrittlement. The hydrogen present in the flame or atmosphere at high temperature reacts with the oxide, yielding metallic copper and water vapor, steam. The steam bubbles exert high pressure in the metal structure, leading to cracks and joint porosity. Oxygen-free copper is not sensitive to this effect. However, the most readily available grades, for example electrolytic copper or high-conductivity copper, are. The embrittled joint may then fail catastrophically without any previous sign of deformation or deterioration. Preform: a brazing preform is a high-quality, precision metal stamping used for a variety of joining applications in manufacturing electronic devices and systems. Typical brazing preform uses include attaching electronic circuitry, packaging electronic devices, providing good thermal and electrical conductivity, and providing an interface for electronic connections. Square, rectangular and disc-shaped brazing preforms are commonly used to attach electronic components containing silicon dies to a substrate such as a printed circuit board. Rectangular frame-shaped preforms are often required for the construction of electronic packages, while washer-shaped brazing preforms are typically utilized to attach lead wires and hermetic feed-throughs to electronic circuits and packages. Some preforms are also used in diodes, rectifiers, optoelectronic devices and components packaging. See also, Braze on, Cupro Braze, references. Bibliography, Groover, Mikkel P. Fundamentals of Modern Manufacturing, Materials Processes, and Systems. John Wiley & Sons. ISBN A978-81-265-1266-9. Schwartz, Mel M. Brazing. ASM International. ISBN A978-0-87170-246-3. Further reading, Fletcher, M.J. Vacuum Brazing. London, Mills and Boon Limited. ISBN A0-263-51708. Exa, P.M. Roberts, Industrial Brazing Practice, CRC Press, Boca Raton, Florida, 2004. Kent White, Authentic Aluminum Gas Welding, plus Brazing and Soldering. Publisher, TM Technologies, 2008. Andrea Cagnetti Experimental Survey on Fluid Brazing in Ancient Goldsmiths Art Euro International Journal of Material Research DOI 10.3139/146.101783, 1, External links, The Brazing Guide, Brazing and Soldering Aluminum, Copper, Brass, etc. European Association for Brazing and Soldering, Braze Welding.